So, in our previous podcast, we got as far as explaining how one particle exerts a pressure on one wall of a cube in one direction. In this podcast, we'll explain how lots of similar gas particles exert a pressure on this same wall. The mass of these many particles is easy enough to show. If one particle has a mass of m, then many particles, n, have a mass of n times n. The complexity comes when we work out the velocity of these particles. An ideal gas undergoes Brownian motion. All the particles in an ideal gas are free to travel in any random direction. This means that the velocities of these gas particles are randomly distributed as well. In order to have a semblance of a velocity that we can use in our equations, it needs to be an average velocity. But there's a problem with an average velocity. If gas particles are truly random, then there will be as many particles going backwards as going forwards. The arithmetic mean of these velocities would be equal to 0. So instead of an arithmetic mean, we take a root mean square. Take all the velocities in the x direction, square them, take a mean of these, and then square root them back to give a value. However, because we have effectively removed the direction component of these velocities, we can no longer call it an average velocity. It is now an average speed. It is, however, still in the x direction. We have removed the direction element of the particles, but we have only been looking at the particles that were initially travelling in the x direction. What we've done is turn any particles that were going backwards into forward-moving particles, and averaged all of them. The pressure of all the n particles in the x direction is equal to the mass of these particles times the root mean square of the speeds of these particles in the x direction, divided by the volume of the box. Px equals nmv rms squared x divided by v. Now we need to apply this equation to all three directions in the box.